So now that we can take the derivative of a function, sometimes we might want to go backwards. So if we have a derivative of an unknown function, we want to find the original function that it came from. So let's say we have the derivative of s is 32t, and we want to know what s is, the original function that relates s and t. So remember that the derivative of this function y equals x squared, where a is a constant. To find the derivative, the derivative is 2ax. So it looks like we took the exponent and put it in front and then subtracted 1 from the exponent. So to go backwards, if we start with 32t, it seems like we should raise the exponent and then divide by the new exponent. So let's try this. So we raise the exponent to 2 and then divide by 2. So we get 16t squared. And if we differentiate 16t squared, we go back to 32t. So it seems like this is the correct formula for the original function. But we're not done yet. So remember that the derivative of any constant is 0. So that means if there's a constant term in the original function, we won't see it in the derivative. It'll get lost when you differentiate. For example, 16t squared plus 2, or if it's plus 57 or plus 2 million, plus any constant, the derivative of all of these functions is still 32t. So how do we know which original function is the correct one? And well, the answer is that right now we don't know. So what we do is, to make up for this fact, we just add an unknown constant c when we find the original function. Now this c is called the constant of integration. So instead of writing 16t squared, we write 16t squared plus c. So the c makes up for the fact that plus any constant, the derivative will still be the same. So this process of going backwards, or from studying from the derivative and then finding the original function, this is called antidifferentiation, or sometimes integration. And more specifically, the original function is the indefinite integral. We'll learn about another type of integral later. So this original function is called an indefinite integral or an antiderivative. So far from this example, we found that if you have the derivative of a function is equal to some constant a times x, the independent variable, to find the integral, you raise the exponent of x to 2 and then divide by 2. And then, of course, you add the plus c. And that's what we did here. And we also know that if we have a function y equals bx, the derivative will be b, just the coefficient. So that means if we start with the derivative equals b, we can integrate to get the y equals bx plus c. So every time you find a new derivative of a function, that means you can also go backwards and find, if you start with the derivative, you can go backwards and find the original function. So every time you learn a new differentiation formula, you're actually learning another integration formula as well. And just like with differentiation, if we have a polynomial that is the sum of these types of functions, if we want to take the antiderivative, we can take the integral of the terms individually. So if we have 3x plus 7, to integrate that, we do each term individually. So this one becomes 3 over 2x squared, and this one becomes 7x. And then plus c. So now let's look at how you can apply differentiation and antidifferentiation to some problems of motion. So we're going to be looking at motion along a straight line. So, it's called one-dimensional motion or rectilinear motion. So let's say we're 400 feet above the ground and we want to know how long it will take an object to reach the ground if we just drop it. So to do this, you have to know that all objects near the surface of the Earth have a downward acceleration of 32 feet per second squared due to gravity, if we ignore air resistance. So we start with this number, acceleration equals 32. And also before you start a problem, you have to determine which direction is going to be positive. So we can say that up is positive and down is negative, or we can say that downwards is positive and up is negative. So for this problem, I said the acceleration is positive, and since this acceleration is downwards, that means I'm taking downwards to be the positive direction and up to be negative. Now, you can do either way, but you have to be consistent within the problem. So from the acceleration, we find the speed function. So acceleration is the derivative of speed. So to get speed from acceleration, we integrate it. So this is just a constant. So to integrate, we just add the independent variable. So we get 32t plus c. And now we can solve for the c if we know something about the object at the initial time. So for example, in this problem, we dropped a ball. So we know that if you just drop something, it's initially starting out with 0 speed. So we know that when t equals 0, the speed is going to be equal to 0. So we can use that to solve for the c, and we find that c is also equal to 0. So the true speed function is v equals 32t. So now we integrate again to get back to the distance formula. So integrating this will get you 16t squared plus c again. And we can again solve for the c if we know something about the initial conditions. So we know that when t is equal to 0, it's at the top of the, wherever we are, at 400 feet above the ground. So here we need to choose, how we're going to define our coordinate system. So if we say that the point we dropped the ball at is s equals 0, the origin of a system, then we can solve for c by plugging in t equals 0, s equals 0. And so you find that c is equal to 0. But you don't have to define the point where you drop the object as s equals 0. For example, you could say that the ground is s equals 0, and that means the point is standing at 400 feet above the ground is going to be s equals negative 400 if you define down to be positive and up to be negative. So now we have the distance formula. This tells us at any time t, what is a distance from this point where we dropped the ball. So all we have to do to find out how long it takes to reach the ground is we plug in s equals 400 and solve for t. So this information about v and s at t equals 0, remember we said at t equals 0, s and v are equal to 0, and that allowed us to solve for the c. So these are called the initial conditions or initial values. So let's do the same problem, but taking different directions and a coordinate system. So this time, let's say upwards is the positive direction and down is the negative direction. So that means acceleration, since it's downwards, it's going to be negative. So we start with a equals negative 32. And then when we integrate that to get speed, negative 32 plus c, solve for c equals 0 using the fact that the speed is 0 when time equals 0. And then integrate this again to get distance is negative 16 squared plus c. But now a c value is going to be different if we take a different coordinate system. So here we said that s equals 0 is the ground. So that means initial position, 400 feet above the ground, is going to be s equals 400. So initial conditions are changed in this problem. And so now a c is equal to 400 instead of 0. So now let's look at what this function s represents in this problem. Remember, in the other example, s represented the distance traveled from our initial position. But here, when t equals 0, s equals 400. So does that mean we already traveled 400 feet at t equals 0? No. So here s represents something different than the distance traveled. It denotes the object's height above the ground, because we took the origin of the coordinate system at the ground. So when t equals 0, s equals 400, which means it's 400 feet above the ground, which is s equals 0. So this function denotes the object's position relative to the origin of a coordinate system, which is at the ground. And also, v no longer represents speed, because you can't have a negative speed. But this is something called the velocity. Velocity is like speed, but with a direction. So the velocity can tell you which direction am I going and how fast am I going. And the direction component of the velocity is given by the positive or negative sign. So if velocity is negative 32, that means I'm going 32 feet per second, downwards. If it's positive 32, that means I'm going 32 feet per second upwards. So one more problem. Suppose we start on the ground and we throw an object up with an initial velocity of 128 feet per second. And the object's going straight up. So if we define upwards to be the positive direction, and the origin of a coordinate system to be the ground, so let's find the equations of the object's motion. So like always, we start with a equals negative 32, because it's only under the influence of gravity. And so integrating that, we get negative 32 plus c, and this time we have an initial velocity. When t equals 0, v equals 128. So a c is going to be equal to 128 if we plug these initial conditions into this equation. And then we integrate again to get the position function. So negative 16 squared, t squared plus 128t, from this term, plus c again. So when t equals 0, s equals 0 because we're studying at the ground. So c for this one is going to be equal to 0. So let's think about what the object's going to do. When we set at the ground and we throw it straight up, so obviously it's going to hit some point that it's maximum, and then it's going to fall back down. So at this maximum highest point in the object's path, its velocity is going to be equal to 0. And that's because it's transitioning from going up to going down. When it's going up, the velocity is positive, and when it's going down, the velocity is negative. So in between is 0 when it stopped moving and it's at its highest point, ready to fall back down. So we can solve for when this occurs by setting velocity equal to 0 and solving for t. So we find that at t equals 4 seconds, the object is at its highest path, and then we can find how high that is by plugging 4 into the position function. So we find that at t equals 4 seconds, the object reaches its maximum height of 256 feet.